In 2014, an article was written on Business Insider titled, "There's a Shocking Connection Between Eating More Chocolate and Winning the Nobel Prize." And the article proceeds to show that there's a correlation between the amount of chocolate consumed per capita and the number of Nobel laureates per 10 million people for various countries. Here's the graph that they produced in the Business Insider, and we can see up here they've calculated an R value of 0.791 with a p-value of less than 0.0001. There's a very strong positive correlation for chocolate consumption and Nobel laureates. So taking this into consideration, back in section 10.1, there is an example with the data that we could use. So eat more chocolate and win a Nobel Prize. We've got a listing of data here, the chocolate in kilograms per capita and the Nobel laureates per 10 million people for various countries. And in 10.1, we would run a hypothesis test for linear correlation. But now in 10.2, we've already run that hypothesis test. And we got an R value, because we were using more data than the article was using. We got an R value of 0.801. We're going to talk briefly about something called explained variation. If we square our correlation coefficient, R, and get R squared, we get something called the coefficient of determination. The coefficient of determination is a measure of the dependent variable that is explained by the regression line and the independent variable. Ultimately, R squared is the proportion of variation in y that's attributed to the linear relationship between x and y. The remaining proportion is by chance. So if we're looking here at the 23 pairs of chocolate Nobel data, and we got the R value of 0.801, we want to know what proportion of the variation of Nobel laureates can be explained by the variation in the consumption of chocolate. In order to find that variation, we need R squared. So we'll pull up our calculators, 0.801 squared, and we get 0.641. R squared, 801 squared, 0.641, which would lead 64.1% of the Nobel laureate variation is explained by the chocolate. We don't want to confuse R with R squared. Standard deviation and variance are related, but they are different, and so are the linear correlation coefficient and the coefficient of determination. If we are able to get a significant linear correlation with data, the next step is to determine the linear equation that would best model that data. We call this the regression line, or the line of best fit, or the regression equation. We are trying to find the smallest differences between the observed value and the predicted value. So we can see here in this graph, we have the predicted values are all along the line, the actual regression line, and the observed value could be slightly off of it or it could be on it. And so the idea is we want the smallest amount of these differences. We're actually looking at the smallest amount of the square of these differences, but we're not going to be calculating this. We're going to let technology take care of this for us. Pointing out the form of the regression equation, y prime equals a plus bx. You might also see y hat equals a plus bx. So this prime versus hat depends on the notation of a textbook. Just know that either of them are indicating the regression equation. And we use y prime and y hat instead of y because y is representing the observed values. These observed values are the y values. The predicted values that fall along that line are the y hat values or the y prime values. It actually turns out that to calculate the values for the regression equation, specifically the y-intercept, which in statistics books is usually called A, and the slope, which in statistics books is usually called B, there's some pretty simple formulas that we can use to calculate them. Recall in algebra, y equals mx plus b. M is the slope in this form, and b is the y-intercept from algebra. Unfortunately, statistics has changed that notation, so the b in statistics means something different than the b in algebra. The big picture, all you have to remember is the slope gets multiplied by x, and the y-intercept is by itself. The slope will always be the value multiplied by x, and the y-intercept will always be by itself added to it. So there are some simple formulas for our slope that we'll be using, and for our y-intercept. So slope, given by b, is equal to our correlation coefficient times the standard deviation for the y values divided by the standard deviation for the x values. Once we calculate the slope, we can use the slope to calculate the y-intercept. The y-intercept is given by the average of the y's minus b times the average of the x's. So when we have this data, we'll find the means and the standard deviations, and then we'll use those to calculate a and b for our linear regression equation. We usually round a and b to 3 significant digits, and so that's what you'll see me do here. So now we're going to try to find the regression equation for the chocolate versus Nobel laureates. We've got some formulas up here to remind you how to calculate the correlation coefficient, standard deviation, and the means. Pulling up Excel, we have this data listed in Excel. We ran a linear correlation test to determine that the amount of chocolate is linearly correlated to the Nobel Prize winners. Let's see if we can come up with a regression equation that we could use to possibly predict. Even if it is a silly connection, let's just try it. So I have a table of values here that we're going to use Excel for. You can see the Excel functions, and the functions in Excel work the same as in Google. So if you're using Google Sheets, these formulas should be the same. I do want to make one small correction here. We should make the standard deviations stdev.s. So stdev.s. Excel will default to the sample standard deviation, but we want to make sure that that is the case. So let's go back to Excel. Here we have that same data, and we have the results from our original linear correlation hypothesis test. Down here on the bottom, we're going to calculate the mean and the standard deviation for each of these columns. So standard deviation .s, and then I'm going to take these formulas and drag them over so that they calculate it for y. So we have x is the first column and y is the second column. And now I'm going to come over and calculate my slope and my y-intercept. So that I have all of these formulas on the same place, I'm going to recalculate my correlation coefficient. So I recalculate my linear correlation coefficient so that I have all of my relevant information right here in front of us. B is given by R, so R times standard deviation of y divided by standard deviation of x. I'm just pulling up this really quickly. We can see R times S sub y over S sub x. Hit enter and we get 2.493. A is given by the average y's minus b times the average x's. And we get negative 3.366668. One small thing to note, These are formulas that have been simplified from that least squares process. There's actually a much larger formula that could be used to calculate the slope and the y-intercept. Those formulas leave you open to making a lot of careless errors. Since these formulas are much simpler, that's why we'll use these. 2.493. All right, now copying over the values from Excel, I've put them up here in our table for our standard deviations and the averages. And then I've also included our slope and our y-intercept that we've calculated. And now we can use these to form our linear regression equation. We can say that y hat or y prime is equal to negative 3.367 plus 2.493 times x. And if you round your correlation coefficient to 0.801 instead of using the entire value like I did in Excel, you might get slightly different answers, particularly in the second or the third decimal places. So there could be a possibility of getting slightly off in the calculations, depending on how you're rounding. Know that the regression equation is an estimate of the true regression equation for the population of paired data. We're only looking at one particular set of sample data, so if we were to take more samples or use a different sample, we could get a different linear regression equation. We can use regression equations to predict the value of one variable given some specific value of another variable. But we need to make sure that we're being mindful of the following. If the regression equation does not seem that it's useful for making predictions, don't use it. If we try to get a linear correlation and there's not a linear correlation, then we shouldn't need to form a regression equation. And in that case, we would just use the sample mean for the best predicted value, particularly the sample mean for the y values. The best estimate we would have for any value if we don't have linear correlation is to just use the sample mean. If it's a good model, we can use the linear regression equation for predictions, and we want to make sure that line falls on the scatter plot pretty well, and we need to do a scatter plot for our Nobel Prize data. We'll do that in a moment. We don't want our predictions to go too far outside our X value sample data. Going outside our sample data is something called extrapolation, and if we go too far away, it could be that the model changes, that it's no longer linear. So we want to stick either within the range of values for our X values that we have, and maybe go only slightly outside it. Let's come back to our data and create a scatter plot and also use Excel to check our linear regression equation. So we'll select our data, insert, scatter plot. Looks pretty linear. Well, it's kind of messy, but looks like there seems to be a correlation there. Let's get some chart elements on here. We'll have the axes. So our X values is chocolate in kilograms per capita. And per capita is just a fancy way of saying per person. It's actually Latin, per capita. And then on our Y value, we have the number of Nobel laureates per 10 million. So here we have our scatter plot. We can come into our chart elements. Remember, on a Mac, you can come up here to add chart element. Add a trend line. We've got a nice linear trend line. And then I'm going to go to more options and the bars. Scroll all the way down. Let's display the equation and the r squared value. I'm going to move it so we can see it. And sure enough, 2.493, negative 3.3667. Those were the values that we got in our calculations, which was awesome. R squared is 0.641, which is what we got earlier in example 1. And I'll take our scatter plot and paste it right up here next to our data. And there you have it, linear correlation and linear regression.